Hi everyone, I'm Kedong, the author of this work, and Professor Wang is a corresponding author, and I'm happy to be here sharing this work with you guys about the password security. So let's get started. Textual password is the most prevalent authentication, due to its they are easy to use, low cost, and easy to change. I know there are some other alternatives have been proposed, like Apple, Microsoft. They try to use some passwordless authentications, but still, I think these methods are similar to of the future, and users may use these methods for their new accounts, and but still, these methods have a little impact on their old accounts. So, yeah. Credential stuffing attack is the most prevalent realistic threat for online web users. There are rarely some reports showing that web users have maybe 80 to 107 passwords on average. The latest data breach investigation report shows that 77% web attack is credential stuffing attack. And most existing models, they might use some different ways or some model architectures, but they have one common but intuitive idea. They treat the conditional password guessing model is a process of predicting the added operations based on the old password. So, for example, it's showing the right part of this slide. Suppose we got the password 1, and we can input this password into the model, and the model will output the sequence of added operations. We can apply this sequence operation to the old password to generate the target password. So there are some existing issues. The first one is existing models. They need to filter the training set while they overlooking their password pairs. As shown in this table, current similar metrics like added distance or cosine similarity, same employee could lead to filtering some actually similar password pairs, and these models could possibly not accurately characterize users' password use behaviors. The second one is some existing models normally employ some heuristic method to mix popular password. And they try to use this way to characterize users' reuse behaviors, specifically reusing some popular password or segments. The third issue is the number of atomic added operations are so large, and we can see, so it will cause the prediction space is at each time step is too large. Normally, you will use all printable ASCII characters as prediction space. Its space size is less than 100, and while the size of prediction space could be 2,000, much larger than the former case, you will adopt the atomic added operation as the prediction space. And the fourth issue is the inefficient utilization of the old password. So the normal ones, they normally only generate new characters based on this model, such like that, and sometimes they overlook the copy operation from the old password. So overall, considering these existing issues, we propose our work based on the three thoughts. We try to directly predict character sequence of the target password, and we model a new conditional password guessing probability. We consider both copying characters from the old password and generating new characters based on this old password. So in that case, we propose our new model, PointerGuess. We use the attention score of the characters in the old password to generate the conditional probability of the copying characters. Of course, to be more effective, we employ a mask attention module to modify the attention score so we can focus on the valid characters only, ignoring some like placeholders or some useless signals. As for the conditional probability of generating new characters, we still employ a normal decoder like long short-term memory model. And furthermore, we employ a weight factor, which is also a learnable parameter to weight sum these two conditional probabilities. So to facilitate the generation process of pointer guess and better utilize the ability of GPUs, we specifically implement batch beam search algorithm for password generation. The first step is we choose the batch size before generating guesses, and then we choose the global top K guesses for each user, which is also named as the maximum guessing attempts for all users. Lastly, we choose the last top K candidates of each user's beam search process. So in this way, our generation algorithm could achieve 3 to 4 times faster than the normal generation process. Of course, to comprehensively compare our model with existing models, we employ 11 real-world data sets, including 4 Chinese, 4 English, and 2 large-scale mixed data sets, and to conduct 12 attack scenarios, and including 4 Chinese, 4 English, and 4 mixed, of course. And to make sure our experiments are reproducible and to make sure all normal attackers can use this method, and we run our all experiments on NVIDIA 3019, and everyone can have it. Yes. So here's our experimental results. Overall, our pointer guess achieved the best performance compared to other existing methods, particularly while we excluding identical password pairs in the test set. The average success rate of pointer guess is 38.37%, on average higher than its foremost counterparts. And we can see pointer guess inherently owns the ability of generating popular passwords. And our pointer guess is 3 to 5 times faster than the other model. While generating guesses, we can almost generate 10,000 guesses per second, and the model size of pointer guess is just 2.26, which is much less than other 2 models. So to better investigate the target passwords cracked by these 3 models, we choose some cracked examples as shown in the upper table to demonstrate the differences of 3 models' cracked passwords. We first analyze the overlap ratio of pointer guess, parse ID, and pass to pass. There is 34.3% overlap rate among 3 models, and more importantly, that we can observe is pointer guess have much higher independently correct password rate, which is 16.7%. Then we also investigate the similarity distribution of these 3 different models. We employ spatial distance-based metric and sequence alignment-based metrics to try to analyze these 3 models' correct password, the distribution of these 3 models' correct passwords. So then to better understand the impact of the different parts of our model architecture, we first compare pointer guess with our baseline plain stack, which removes the pointer mechanism and keeps other parameters unchanged. The results show that there are 2 important advantages that pointer guess have. The first one is it can delete or just add some rare substrings. For example, like this example, our pointer guess can just delete the last 5 letters, 5盘, to generate the target password. And the second one is the pointer mechanism empower our model can particularly crack some password pairs with with a larger similarity differences. Moreover, we also investigate the impact of hidden dimensions on model performance, as shown in the right figure. The figure shows that the model dimension barely impacts the model performance. So after this work, we have a question is, can we use each victim's multiple linked passwords to more effectively crack their target? I think there is a correct answer, and that's why we propose a multi-source pointer guess, which employed a multi-encoder module. We also construct these 2 attack scenarios, 13 and 14, and we employ 6 data sets, 3 Chinese and 3 English data sets. Our results demonstrate the effectiveness of utilizing multiple old passwords to crack the target password. And we can show these figures, and within 100 guesses, its average success rate in cracking is 17.20% higher than pointer guess in the scenario 13, and 38.78% higher in scenario 14. So after all, we have other explorations about this work, and we try to employ our pointer guess to evaluate some the password strings personalized. We propose a personalized password strings matter, and based on the user's provided password. And we also try to apply pointer guess into C3 services. For example, we generate a set of variants based on the given password, and we try to hide the user's target password into this fake password to protect it. Yeah, so that's all. Thank you.